So pressure affects our weather. A lot of our weather is due to variations in pressure. You get high pressure systems and low pressure systems. We can predict the weather in part because of that. So high pressure is usually associated with clear weather, low pressure with unstable weather. And so you can look at the barometric pressure. You know, today it's 29.79 inches. And so that's relatively low, but not super low. It's kind of medium. So the number of gas particles in a given volume decreases with increasing altitude. So as you go higher and higher above sea level, the air gets, we say, it gets thinner, right? There's not as many molecules in the same volume. So the concentration of air goes down, the pressure goes down. So atmospheric pressure decreases as you go up in elevation. And that's why, you know, you go high in the mountains and you get out of breath more easily, because there's just not as much oxygen in the air, and so you have to breathe a lot more to get the oxygen that your body needs. If you keep going up, you'll get to a point where you're going to pass out because there's just not enough oxygen to sustain life. So pressure is related to the concentration of a gas or the density of a gas. Density is mass divided by volume. So if you have a larger number of particles in the same volume, it's going to have more mass. This is going to be more dense. It's going to have a higher pressure. You can also think of that as concentration. Again, amount per unit volume. Fewer gas particles in the same volume, lower pressure. This is, you know, the closest to biology we get in this lecture. So here we've got an ear, right? So pressure imbalances cause your ear to pop. So you go up in an elevator, not in an elevator, in an airplane, or go up in elevation. That's what I was trying to say. Go up in the mountains, high elevations. The external pressure is reduced. There is air inside your eardrum. Your eardrum is, you know, choked up about eardrums. The eardrum is not permeable to water or air. When you get water in your ear, it's just stuck out here. It's not actually going all the way in. But there's air inside and there's air outside. If the outside pressure is reduced, the inside pressure is going to cause your eardrum to bulge outward, and that doesn't feel good. And your body takes care of that by this pressure will cause your eustachian tube that goes down into the back of your throat to open up, and you experience that as a popping sensation. Your ears pop. And then you're like, oh, okay. And yawning or chewing gum will help to open the eustachian tube and make that popping go a little better. If you've got a bad cold, oh, you're going to be in trouble. Your ears are going to hurt. They're not going to pop well, and it's just miserable. The opposite happens when you come back down. Now you've got low pressure inside, high pressure outside, and so they have to pop the other way. Any questions about that? How do we measure pressure? Well, measuring atmospheric pressure, we use a barometer. Of course, now we have electronic instruments that measure this. I mean, we've got this little weather station here. This has a barometer in it that's measuring the atmospheric pressure in the room. That does not involve mercury. But those are kind of hard to understand, and so we're gonna look at the original barometer because it's simple. So the original barometer was invented by a guy named Torricelli, and I think it was back in the 1600s. So this is like way before electricity, way before we knew what atoms were, any of that. So he took a glass tube full of mercury and inverted it in a dish of mercury. And what he observed is that no matter what he did, how big the tube was or how narrow, the column of mercury was always the same height. What's happening here is atmospheric pressure is pushing down on the mercury in the dish, which helps to support this column, because in order for this mercury to come out, the level in the dish has to go up. So we've got atmospheric pressure pushing down. But in the tube, we have gravity pulling down. And so we have these opposing forces. Yes?
Does that depend on the size of the dish?
It does not depend on the size of the dish either. Nope, it doesn't. It's kind of weird that way, huh? What we have above the column of mercury is a vacuum. Now, if you do this with water, and you take a long tube and you fill it with water and invert it in a dish, it'll stay full of the water. You won't see this empty space because water is much less dense than mercury, about 13 times less dense. The height of this column of mercury is always about 760 millimeters, or 29.92 inches. And it's actually just measured with a ruler, right? So this is very low tech. There's no technology here. He observed that if you take this thing and you walk up a mountain, that the column of mercury gets shorter and shorter and shorter. As you go up in elevation, atmospheric pressure is less. And so the atmospheric pressure can support only a shorter column of mercury. You walk it back down the hill, the column goes back up. It's this atmospheric pressure. So the average atmospheric pressure at sea level is 760 millimeters of mercury. That's a weird pressure unit, right? A length of an element. It comes from this barometer. So you measure the height of the column of mercury using a ruler in millimeters, 760 millimeters of mercury. That's the pressure unit. We also have a fancier sounding name for that, one torr, named after Torricelli. A torr is exactly the same as a millimeter of mercury. We use both of them. Any questions? Do you know why we don't use water in barometers? Because the barometer would have to be about 30 feet tall. Because that's about 32 feet is atmospheric pressure can support a column of water about 32 feet tall. Not real practical. So mercury works better. These are other pressure units. We're going to use torr, and we're going to run into inches of mercury. That's just measuring the column using inches instead of millimeters. And then the unit atmosphere. So an atmosphere is the average pressure at sea level. Sea level is chosen because that's easy. So 1 atmosphere, and all of these are equal to each other. So 1 atmosphere is equal to 29.92 inches of mercury. It's equal to 760 torr. Exactly, that one's defined that way, so exactly 760. 14.7 psi, 101,325 pascals. That's the SI unit. We don't use that much in chemistry. So converting pressure units always involves just one step, so it's really pretty simple. So let's do this example. Your local weather report announces that the barometric pressure is 30.44 inches of mercury. Convert that to psi. So we've got a unit that we're starting with and a unit we're trying to find. So we're starting with 30.44 inches of mercury, and I'm going to multiply by one factor. I want psi, so I put that on top, and I'm getting rid of inches of mercury, so I put that on the bottom, so the units cancel out. The conversion factor comes from either the table on the previous slide, or what I'll give you in an exam situation would be this second line. I'm not going to give you this first line because I want you to memorize that. An atmosphere is 760 torr exactly, which is 760 millimeters of mercury exactly. That's one number you have to remember. And we use it so often that it really is to your advantage to memorize that. So looking at this, 1 atmosphere equals this, equals this, equals this. These are all equal to each other. So I can pick out whichever 2 I need and make a conversion factor. So 14.7 psi is equal to 29.92 inches. I don't have to go from one to the other to the other. So 14.7 psi, that is not an exact number. and 29.92 inches of mercury, also not an exact number. $30.44 times 14.7 divided by 29.92. So my calculator says 14.955 PSI. PSI stands for pounds per square inch, and so that's going to round for 3 sig figs to 15.0 PSI. Any questions? That's the unit that we use to measure the pressure in our tires, car tires, bike tires, etc. We have all these different pressure units because they're useful in different situations. Why am I using 3 sig figs? That's a good question. These, other than the 760, are not exact conversions, and so 14.7 is only 3 sig figs.
Even if we started with the 30.4?
Yep, even if you start with the 30.44. What I don't like about this book is we know that to 4 sig figs. Why not write it in there? It should be 14.69. This isn't good unit converting. You shouldn't have your unit conversion causing you to lose significant figures. It's dumb. Any other questions? What if we want to measure pressure inside of a container, not just atmospheric pressure? Well, then we're going to use a manometer. So a manometer uses the same principle with liquid mercury in a tube. So here we have our pressurized gas, and here we have a tube. It's connected to a tube filled with mercury, and the end of this tube is open to the atmosphere. If both sides were open to the atmosphere, then this column of mercury on this side would come down, and that one would go up until they get to the same level, right? You think of water in a hose, and it's going to stay level, right? Because gravity's going to pull on it equally on each side. Here, this side is connected to a container. It's not open to the atmosphere. So we have pressure of the gas pushing down on this side. We have atmospheric pressure pushing down on that side. This side is lower. That tells me that this pressure is larger. This one is winning. This one pushing down is beating out the atmospheric pressure. So this is going to tell us the difference between the pressure in the container and the atmospheric pressure, which you would have to measure that somehow. The difference in those pressures is the height of the column of mercury. Any questions? If this was lower in pressure than outside, the column of mercury would be higher on this side and lower on that side. So the side that has the lower mercury is the higher pressure. It is pushing down. You think of blowing in this tube. If you blow on this, you're going to push the mercury up to the other side. If you let go, it's going to come back and be level.